think Deepa, we can start now, right?
Yes.
Yes, Kate.
Hello, everyone. Very good evening to one and all present here. This is Saturday, 12th of August, and we are here to listen to Rohini, who's an undergraduate and quantum computing enthusiast. So let's give a round of applause to Rohini. We welcome you, Rohini, and Deepa. And can you introduce our speaker for the day?
Sure. Okay, once again, good evening all. I'm Deepa Vinod and Academic Council of MyQuantum. Here we are with another section, that is Quantum Entanglement. Welcome you all. And your valuable cooperation and feedback are greatly appreciated as they contribute to the continuous improvement of our upcoming sections. And a few words about MyQuantum. MyQuantum, that is MyQuantum Technology, is your partner in quantum computing journey, providing innovative quantum computing training and solutions. MyQuantum is a repository of world-class knowledge and wisdom contributed by the best minds in the field of quantum computing. MyQuantum operates across the globe through its vast network of affiliates and partner organizations. MyQuantum provides a wide range of offerings, including training, certification courses, research opportunity, and consulting services. And I'm really proud to introduce our speaker and a few words about her. She's Rohini, and she's an undergraduate in PhD College of Technology, Coimbatore. That's this fall. She's going to just join. She's majored in maths, physics, chemistry, and computer science, specialized in Python in her high school. Her journey into quantum computing began with the Q by Q Introduction to Quantum Computing in the year 2022. The course was engaged for 8 months, where she learned from the basics of quantum to some of its important applications and completed the course within the grade of 100%. Proud of you, Rohini. Next, she started preparing for the IBM Qiskit Certificate Associate Developer exam and came out with flying colors. Again, she joined the Girls in Quantum as the Indian ambassador as international organization which brings together quantum resources so as to make quantum learning accessible for everyone. She is also a Qiskit Tamil book translator where she have translated and improved over 15,000 plus words and counting. She have also participated in various IBM quantum challenges. These are a few appreciating and proud words about her. And now I hand over to Rohini so that she can start her section. Thank you, everyone.
Thank you so much for the introduction. And yeah, myself Rohini, as already ma'am said. So those are a little bit things about me, and maybe we could get into the session. So yeah, so I just now completed my 12th grade, and I'll be joining college from the August. So yeah, that's it. I'll just share my screen, and we'll get into the session directly. Yeah, so I'll just give an outline. So first we'll have a PPT introduction about quantum entanglement on like what are the concepts about it. We'll see some of its visualizations and more. And then we'll also have a lab session where we'll go into IBM quantum experience. We'll open the lab and we'll run a few slides and we'll see how quantum entanglement works with the code also. Okay. So yeah, so first I'll start with the PPT presentation. I think my PPT is visible. Okay, so I'm beginning it. So yeah, this is just the introduction. So we are going to have a topic on quantum entanglement. It's one of the most fascinating properties of quantum mechanics, I would say, because it's a very unique one, only related to quantum. So among the 5 properties, my favorite one is quantum entanglement, of course, and not just mine. It's really spooky and it's interesting, and you'll find it more awesome. Like you would be amazed to see what the property is and that's about it. So yeah. So just a definition about quantum entanglement. A property in which a pair of particles is generated in such a way that the individual quantum states of each are indefinite until measured, and the act of measuring one determines the result of measuring the other, even when at a distance from each other. So like maybe you would think this is so big, and no, I'll just make it simple in the further slides. Just as a definition I wanted to give to you. So in the upcoming slides, we'll see what really it is. Okay. So yeah. So now we'll understand quantum entanglement. Okay. So I'm here. Okay. I'm in Kanpur and I like tea. Okay. And my friend, if you can take Elisa. Okay. She's one of my closest friends and she's in South America and she likes cold coffee. Okay. So if I'm here and we both are entangled. Okay. We are close friends, right? We both are entangled. Though we are entangled, our thoughts are different. Okay. So my thought is about tea and her thought is about cold coffee. Okay. So like we are opposite spins, okay, for example. So I want tea and she prefers cold coffee, but anyway, we are best friends. So we are entangled in a manner, okay. But she stays in South America and I stay in India, okay. So we are we are miles apart, right? So even though I ordered chai here, even though I ordered tea in some hotel here, she will automatically get a cold coffee there. Interesting, isn't it? So yeah, that's about quantum entanglement. This is just an example. So what I'm coming to say here is, if one qubit is entangled in our in our universe, and there's one more other qubit which is so many universes. You can take universe, you can take a galaxy, a multiverse, or just a country. I'm trying to say the distances here. So it can be miles apart. The distance doesn't matter. If those two qubits are entangled, if you know the position of one, you would automatically know the position of other. Okay. So if they are good friends, they both like tea, they will rotate in the same spin. And if one likes tea and the other one likes cold coffee, they'll rotate in the opposite spin. Okay. That you will know the difference, whether it's going to be the same spin or it's going to be the opposite spin. But the thing you have to concentrate here is, if this qubit rotates, this qubit will automatically rotate. It will automatically spin. Whether in the same or the opposite direction, that doesn't matter, but it would automatically spin. Though those are miles apart, okay? It could be any number of distance, okay? That's what is said in this slide. So when two objects are entangled, they share a defined relationship. That is, when you know one object's state, you would know the other as well, okay? And entanglement can occur between two or more qubits. So it's like not only me and Elisa, it could be between me, Elisa, Deepa ma'am, KG sir, Anjula ma'am, and it could be among, like we are at various distances apart, okay? I'm trying to say here, like if we all are entangled, if I could order tea here, they would also get whatever they prefer. I'm saying about the spin here, okay? They would also rotate according to, as I rotate, they will also rotate, maybe in the same spin, maybe in the opposite spin. Okay, this is entanglement at a kid's level understanding and 18 level old understanding. Okay, yeah. So moving on. Okay, now we'll dive in with the examples. Okay, we'll leave those tea, cold coffee there, and then we'll get into some mathematics. Okay. Okay. First, you could take the state one here. So now we are making a measurement on Q0, okay? There would be one thing called right indexing, okay? So the numbers on this, I'm pointing it, can you see, right? So this and this are Q0 and this 0 and this 1 are Q1, okay? I think I just missed the slide, I'm sorry for that. But I think you're clear with it. This 0 and this 0 are qubit zeros and this 0 and this 1 are qubit ones, okay? So now what we'll do is, okay, now we are making a measurement on Q0. Okay, we are making a measurement on Q0. Making a measurement means like you're measuring it. Okay, we are just seeing if it could affect Q1. Okay, so okay, just by making a measurement on Q0, would we get anything related to Q1? We are just measuring it. Okay, So now, what does Q1, does the above measurement tell us anything about Q1? Okay, so if you're measuring it in if you're measuring the Q0 state here, what would it tell about Q1? It wouldn't tell about Q1 it won't tell about Q1 anything, because here 0 state would be 0, 100% here, and it would be 100% here also in both these states. So in Q1 it could be 0 or 1. Am I clear here? Okay. When we go to state 2, you will understand it more clear. So actually Q1 is still in a superposition. Okay, it is not affected by the measurement on Q0. Okay, we are measuring Q0 actually, but we don't know what it leads to. It could what would Q1 lead to? Okay, it could be 0 or 1, because we have 0 0 plus 1 0 here. Okay, if we could measure here 0, we'd get the 0. If we could measure here, we'd get a 1. So we are still in a superposition state, right? We couldn't fix, okay, this Q1 is going to be what? 0. Q1 is going to be 1. We are not able to fix it, right? Okay, now we'll take a look at state 2. Okay, we are making a measurement on Q0, and suppose we get 0. Okay, so suppose if we get here 0 also, we wouldn't know what Q1 is. It could be 0 or 1. It is in state of superposition, the state 1. But if you take state 2 and if you make a measurement on Q0 and suppose we get 0, you know, measurements can be probabilistic. Okay, they could be 0, they could be 1. That is not in our hands. But in case if we are measuring, take it in our case, okay, we are measuring it and we are getting it to be state 0. Okay, so in these states 0 0 plus 1 1, this 1 by root 2, the which is outside, is for normalization. We're not going in depth of it. I just want you guys to put more focus on the states which are inside the brackets. I mean the brackets. So 0 0 plus 1 1 and 0 0 plus 1 0. Okay, so now we got the state 0. Okay, so between these two states, which state would be Q1 be? Okay, as we got a Q0 to be 0, our Q1 would automatically be 0 as well. Okay, because in between these two states, on the one which has 0 is just 0 0 0, right? 1 1 doesn't have any 0 in it. Okay, I hope I'm clear with it. Okay, now we are measuring the same thing and we get 1. So what would we get Q0 to be 1? What would our Q1 be? It would be 1 automatically, because you know this gets cancelled out. The 0 0 gets cancelled out there. Okay, yeah. So that's it. That's it about entanglement. See, if you could see here, 0 0 plus 1 0 it is, and 0 0 plus 1 1. So if the states are not factorizable, then the state it is said to be entangled. Okay. So yeah, moving on to the next slide. So entangled versus non-entangled states. So entangled states cannot be factorized, that is, cannot be written in the form of two separate qubits. Okay, 0 0 plus 1 1. Can you factorize it? You know, the basic math which we learned in a very few years back for me, like you know, 6th, 7th, we used to factorize it. Okay, so yeah, the same thing. Everyone would be familiar with it. So 0 0 plus 1 1 isn't possible. We won't be able to you know, we take common, we'll write it, and then we'll do the math, right? So here, can we take anything common between 0 0 plus 1 1? Treat it as a simple math equation, you'll get it easily. So between 0 0 plus 1 1, we wouldn't have anything in common, so we couldn't take anything out. Okay, so this is a entangled state. Okay, and measuring on one qubit gives you information on the other. So when you measure Q0 and you got the answer, you could automatically determine Q1 also. Okay, even without knowing even without measuring Q1, we could automatically say it's what Q1 would be. Okay, but in non-entangled states can be factorized. You know, take this equation 0 0 plus 1 0, and what is common here? Okay, Q0 is common here. Okay, we could take Q0 0 as a common. We could separate it. Okay, so yeah, when we take it common, it can it can be written in the form of two separate qubits. Okay, so we won't be able to judge what Q1 would be just on the measurement of Q0. Okay, we have to again measure Q1 again separately. Then those are not entangled. One qubit's measurement wouldn't affect the other. That's the basic definition of entanglement, and we've understood it here. Okay, one qubit's measurement should affect the other. So Q0's measurement would automatically affect Q1. Automatically affect means we'll automatically know what Q1 would be even without measuring it. Okay, but in non-entangled states, that's not the case. You'll have to measure Q0 and you'll have to measure Q1, just the normal measurement, and you'll get probabilistic answers, and that would differ. Okay, I hope I'm clear with the entangled and non-entangled states. Okay, this is a key concept I'll learn, and okay, so I want all of you to see this mind map here. Okay, so all entangled states are multi-qubit superposition states. Okay, entangled states occurs between 2 or more qubits. That's what it means. Multi-qubit superposition states. Okay, it should be in a superposition and it should be multi-qubit. Okay, but all multi-qubit superposition states are not entangled. Only non-fact traceable superposition states are entangled. Okay, so as we saw in the above slides, both of these states are multi-qubit. Okay, and both of these states are in a superposition, but only this is entangled because it's not fact traceable. But whereas this is fact traceable, so it would only be a multi-qubit superposition state and it wouldn't be a entangled state. Okay, so yeah, so if it should be a multi-qubit entangled states and then superposition states and then multi-qubit quantum gates. Okay, it should be for one state to be entangled, it should be in a superposition state and it should be a multi-qubit state as well. Okay, so but all superposition states are not entangled and all multi-qubit quantum gates are not entangled as well. Okay, yeah, moving on. So this is one of the, like why is entanglement having this much hype is because of Sir Einstein. Sorry. So yeah, so Einstein, he owes a lot of respect in the physics world. His discoveries are beyond limits and his inventions, everything. But you know what? Even Einstein, sir, proved to be wrong according to entanglement. Okay, so what happened is one of the foundational insights of Einstein's theory of relativity is the speed of light is a fundamental speed limit in the universe. Okay, we all know this equation, E is equal to mc square. E is equal to mc square. We all know these equations. I'm terribly apart from this equation because just now I completed my 12th standard and I've had enough of the equation already. But okay, we'll I have to learn more. Yeah, I know that. But yeah, so it says is no object or no speed in the universe can be against the speed of light. Okay, speed of light will be the ultimate. It would be the fastest in the whole universe. But what we are seeing here, if one qubit rotates, the other qubit would rotate as well, even though they are miles apart. So Einstein was at confusion. Oh no, this would be against violation of relativity, and this wouldn't be this wouldn't be complete. Okay, he was like shocked. How could if just both of them are entangled, how could they move? What is inside there? What makes them connected like that? Just because they're entangled, even though they're miles apart, how could one's rotation affect the other? He was very sure about that would affect his law of relativity. Okay, so he found quantum mechanics spooky. Okay, one of a great scientist found quantum mechanics spooky. Okay, so it's like all these years we would have been learning what Einstein said, what Newton said, like everything what they found was really correct. In my 12th standard physics, maybe in college also, we take the equations. If you take E is equal to mc square, I use that equation. We didn't prove them wrong. but quantum mechanics did prove Sir also wrong. Okay, so with all due respect to Einstein, sir, so he's a great person actually. So, but even like this is a field where you could be a new scientist. Okay, like if you take the classical physics side, everything, almost everything is discovered. Like if you take one small thing about science and physics, each and everything is discovered. Like even if you go to minute parts, there are things that have to be invented, but invented or discovered. But if you take it to quantum side, everything is under construction. The qubits are under construction, the gates are under construction, the algorithms, everything. So you could this field would create the next generation of Nobel Prize winners and discoveries, I would say, because recently also we received a Nobel Prize for this very own topic, entanglement. Okay, this was the base actually. Yeah. So Einstein just said that, and he's like, no, something must be incomplete about quantum mechanics, and something is there. It's some things. He was like, he directly itself said, hey, one of it's like quantum mechanics is spooky. Okay, so what we have next? So we have John Bell. Okay, he was a scientist who proved Einstein wrong. Okay, Einstein's argument was theoretical actually. Okay, he didn't do any experiments. He didn't move any. He was very confident that quantum mechanics must be incomplete. But John Bell moved from theory to experiment. Okay, in 1960, he showed that we could do an experiment to determine if quantum mechanics was right or didn't have any information that quantum mechanics missed. So what did the experiment say? The experiment was called the Bell test, and we've been doing the experiments for 40 plus years and with increasing accuracy, and every experiment shows quantum mechanics was right and Einstein was wrong, like with all due respect, Yeah, that's fine. So actually the speed is limited to the speed of light actually, his law is also definitely correct. The law of relativity is definitely correct, but the speeds in which the information travels is actually limited within the speed of light. Okay, yeah, I think it's 3 into 10 to power 8 meter per second. Yes, between that speed, these speeds are actually limited, but with those increasing experiments, we wouldn't be going into those experiments. Those are really some advanced concepts. We wouldn't be going into those experiments, like what actually was the experiment and all. We would be learning about, we in the further slides we'll come to know about Bell state. So I want you to show this scientist to the world. So the world already knows him, of course, but here I want to give my thing to him. He was the scientist. The Bell states were named after him. Yeah. The circuit and the truth table. Okay. So first I would want to show you here. You could never factorize any of these 4 states. These 4 states are known as the truth, the Bell states, the 4 Bell states. The only 4 entangled states exist now, and these are those. But if we could increase the qubits, we have for a 3 qubit quantum entangled state, we have the name as GHZ circuit. And yeah, but we are going to see for 2 qubits only, and those are 0 0. Yes, and if it is 0 0, if we have the input as 0 0, we'll get the output as 0 0 plus 1 1. 0 0 here means Q0 and Q1 correspondingly, and then we'll entangle it, and then we'll get the state. If it is 0 1, we have 0 1 plus 1 0. If it is 1 0, we have 0 0 minus 1 1. Kindly focus on the signs as well, the plus and minus. We'll see how it differs in the lab session. Yeah. And 1 1 we have it, if it is 1 1 we have 0 1 minus 1. Okay, a must to create an entangled state. So what 2 states should we require to make a state entangled? That would be a H gate on Q0 and a CX gate on which has its control and thing on Q0 and Q1. Okay, this should exist for all bell states. Okay, and we could add our X gates and Z gates in Q1 and Q0, but this should exist. Okay, this H and CX should exist in the same order. If you could put CX and then H, no, you wouldn't get a you wouldn't get an entangled state. Actually, what does a H gate create? A H gate creates a superposition state, and this CX gate creates a link between Q0 and Q1. Okay, for a state to be entangled, what do we want? We want it to be multi-qubit, 2 states. That work is done by Q0 and Q1, and it should be a superposition. So that work is done by H gate. Okay, that's it. Yeah, but if you put it in the reverse order, it won't work. Okay, you have to create. First it should be a superposition state, and then first you have to create a superposition, and then you have to have the multi-qubit. Okay, that would be the order. Okay, yeah, moving on. So now we'll move on to the visualizations. So these are some visualizations. Okay, these are very for the you could take for the IBM Qiskit developer exam also. For the exam, this topic is a major. It's a favorite topic for the person who's taking the questions. There's a lot of questions coming from this particular topic, entanglement, and in entanglement these visualizations play an important role. Okay, the circuit diagram, the histogram representation, the state vector representation, Q sphere, unitary, like I want to highlight it. That one is a really interesting one and a confusing one too, but we'll see it in further slides. We'll just have an introduction about it. And then block sphere representation, this would be interesting too. And then we have plot state city, plot state Hinton, plot state polyvector. Okay, these are some of the minute things, but you will have, like some maybe 1 or 2 questions from plot state city, Hinton, and polyvector. When I had my exam, I had questions from those. So according to my notes. Visualizations. Okay, so for bell state 1, what are all the we'll just visualize circuit diagram, state vector, Q sphere, and histogram here, and the further slides we'll visualize the other ones. Okay, for 0 0, this would be the circuit diagram. So this is the basic entangled state, the H gate and the CX gate. If you just do this, you get your first bell state. Okay, and then if you could take the 0.707 out, like you could take it common, what you would get is 1, 0, 0, 1. Okay, that would be its representation. So 0.707, it's nothing but that 1 by root 2. Okay, I've told you that would be used for normalization. What is normalization? Is nothing but we have this Q sphere, right? Okay, we'll see the the block sphere, right? Its thing is 1 unit. I wouldn't say 1 centimeter or 1 millimeter, 1 nanometer. It's further small, so I'm saying it 1 unit. That pointer, our state shouldn't cross that 1 unit. Okay, so if that qubit is here, it shouldn't cross that 1 unit. Okay, so what I'm trying to say is just for our state to be inside the qubit, we are normalizing it. Okay, so we are just normalizing it using that 1 by root. Okay, just for its size to be in and around 1 unit. Okay, in and around the radius of the block sphere. Okay, the block sphere is where we visualize the qubit state. Yeah. So this is the representation for state vector. So as I said, you can take 0.707 as common. So you'll get 1, 0, 0, 1. And then for Q sphere, if you take this would be 0, 0, 1, 1. Okay, yeah, 0, 0 and 1, 1. And for histogram, it is 0, 0, 1, 1 with 50% of 0, 0, 50% of 1, 1. Okay, everything would be in a 50%. Okay, as it is a histogram, we would have visualized it in Quantum Simulator. So it's giving us the exact result. Quantum Simulator is nothing but it wouldn't be, it would be a state vector simulator, like it would give the exact result. In the lab session, we'll move on to Quantum Simulator, where we won't be running it on the real device, but Quasar simulator mimics like a real device. Okay, like we don't if we have to run it in the real device, it would take a lot of time. Okay, there are many projects running, you know, all over the world. We know that IBM Quantum Experience is used by so many members around the world. We'll have to wait in queue. So if we want to get our results immediately, we can use the Quasar simulator. We'll run it. Okay, there you could see there would be a difference between the 0, 0 and 1, 1. Sometimes it would be 48, 0, 0 would be 48, 1, 1 would be some 50, 48, it would be 52. It should finally come around 100, okay? It should sum up to 100, that's it. So it could differ, okay? For that thing, which has more probability, we'll take that as answer. For the next thing, you could get 0, 0 as the highest with probability. For that, you have to take 0, 0 as answer. That's another thing about quantum. Measurements can be probabilistic. You wouldn't know what one's measurement could fall into. Okay, it could be 0, 0, it could be 1, 1. It doesn't depend on one hand, but it would be 0, 0 and 1, 1. Nothing else. Okay, yeah. Moving on. This is Bell state 2. Yeah, so 0 and 1. So we are starting with 0 and 0, and for to obtain the 1 state, we are putting the X gate here, and then we have our normal, what I say, a must to create an entangled state, the H and the CX gate. And if you take 0.707 out here, what we get, this is the state vector representation. What we get here is 0, 1, 1, 0. Okay. And then 0, 1, 1, 0. Okay, we are getting 0, 1, 1, 0. Actually, in the state vector, the first state is for 0, 0. The second state is for, after the comma, it's for 0, 1. Third state is for 1, 0. And the fourth is for 1, 1. Okay, so it would automatically correspond to it. So the Q sphere is pointing to 0, 1 and 1, 0 here, right? So we would get the same for the state vector also. And then we are measuring it in the histogram. And now if you can see the difference, it's for 0, 1 and 1, 0 with 50% 0, 1, 50% 1, 0. We would measure it in state vector simulator so that we get the exact result. Okay. Bell state 3. So Bell state 3 is, yeah, 0, 0. If you could see the so we are creating for 1, 0, that is for X gate we are putting on Q 0, and for Q1 we have 0 state, and then we put a normal H and CX, and what we receive is 0, 0, like what we receive is 0, 0 minus 1, 1. Okay, 0, 0 minus 1, 1. So what we have is, just because of the sign, the color has been changed, and yeah, 0, 0 minus 1, 1. Okay, I think the color should be shifted here. You know, minus should get the orange color. Yeah. So 0, 0 minus 1, 1. It would be 1, 0, 0, minus 1. Okay, yeah. So 0, 0, 1, 1. The histogram won't show us the phase change. Only the Q sphere would show us the phase change. So you could see here. Yeah. And Bell state 4. Yeah. Bell state 4. So we are creating it for 1, 1 here. 1, 1 means in X, we are having Q0 also in the 1 state, and Q1 also in the 1 state, and then we are having H and CX, and then we are having like 0, minus 1, 1, 0. So 0, 1 in the minus. So I told you, no, 0, 0, 0, 1, 1, 0, 1, 1. So 1, 0, 0, 1 is in the minus state, so we are getting a minus here, and then 1, 0 is in the positive state, so we don't have any minus sign here. That's it. And then again, we're measuring it in the histogram, and we are getting 0, 1, 1, 0, 50%. Yeah. So moving on. Okay. So now we are moving on to the visualizations of the same thing, 0, 0. So now it's going to be plot state city, plot state infinite, plot state polyvector. I just run through these slides because you know this doesn't have much of an explanation like as we had in the before slides. Plot state city would be 0, 0, 1, 1. We'd have those histograms only on the corners of the map, I would say, and plot state hint is similar to that, as we don't have any phase changes. everything is in white here in plot state hinted, and plot state polyvector, it doesn't have much of explanation. For everything is facing upward, but the one corresponding to YY is alone facing downward. Okay, you just have to remember it. There is not more important of an explanation. Polyvector is one of the visualizations of the Bell state. Yeah, and now 0, 1 plus 1, 0, we'll have these histograms in the middle, and then as we don't have any phase differences, the same thing in the middle with white spaces, but we have ZZ down here, okay? And Bell state 3 also. In Bell state 3, what we could see is we have a minus state, okay? So for the minus state, we have the black color here. Is it visible? So yeah, we have the black color here, and we have two histogram pillars down. Okay, you could see the 3D thing there for the above two. For the above two visualizations, we have the histograms at the top only, and we have the white thing only. But for this, as we have a phase change, we have it at the top and we have it at the bottom, and here we have it. We have white and black with everything in the corner, and we have XX facing down. Okay. State 4, similar. 0, 1 minus 1, 0. We have everything in the middle with two states facing down, two histogram plus facing down, and everything in the middle with black and white combinations. Okay, just because we have that minus sign there. Okay, if we don't have that minus sign, we wouldn't have it. If we won't have the minus sign, we would have got the plus, right? We would have got 0, 1 plus 1, 0. If you could take Bell state 2, 0, 1 plus 1, 0. Okay, so it has white spaces, everything in the middle. But Bell state 4 has a minus change, so black and white and everything in the middle. Yeah, and it has II facing upward and rest of all facing downward. This state's polyvector is a bit different. We wouldn't have just I facing down, we would have I facing up and rest of all facing down. Okay, so Bell state 1 and Bell state 3 are similar, Bell state 2 and Bell state 4 are similar, only the minus sign changes. Okay, just because of the change in phase, we'll have some more things like these phase changes. Just to denote these phase changes, we have these histogram pillars down, this black color coming in. Yeah, that's it. So now we'll go into our lab. Okay. Yeah. So I think the lab is visible. So first we are running our slide. These are some imports actually. I hope they run without any problem, because sometimes IBM Quantum experience is a little bit slow. So I've already run them. We could see we have created the first Bell state here. So as I said, we are creating a quantum circuit with the quantum circuit of 2,2 with two quantum bits and 2 classical bits, and then we have H in the Q0, Cx from 0 to 1, and then we are visualizing it using Bell0.draw of MPL, and then we are getting it. Okay, and now if we could measure, see, like we are measuring it using Quasum simulator. As I told you, we are not using state vector simulator, we are using Quasum simulator with a shots of 1000, and then we will measure it to 1000, and now what you're getting is 496 and 504. Okay, so now according to probability 1 is in a higher state. Okay, 496 and 504. Okay, hope you're getting the difference here. There in the histogram we saw 500, but here, as this Quasum simulator mimics the real device, we are getting 496 and 504 with 1 with high probability. Okay. Yeah, and then we are moving on to Bell state. So Bell state 1 will be named Bell 0. Okay, so Bell 0, Bell 1, Bell 2, Bell 3. Okay, we get four Bell states. Okay, now Bell 0 is completed, and now we are moving on to Bell 1. Okay, Bell 1 again we are creating quantum circuit of with two qubits and two classical bits with H in Q1 in H in Q0 and X and then Cx from 0 to 1, and then to create 0 1 state we have X in the Q1. Okay, then we are visualizing it, and then when we run it in the Castle simulator with 1000 shots, we are getting 512488 of 0110. Okay, what we wanted 0110 here, so yeah, so we are getting 512488. Okay, that's it. So this is the visualization from Castle simulator. Yeah. So and then we are bell 0 is completed, bell 1 is completed, we are moving on to bell 2. Yeah, again we are creating a quantum circuit with 2,2, and then we are putting X, we are creating 1 0 here. For the input should be 1 0 here. So Q0 we have the X gate, and then we have the normal H and CX gate correspondingly, and then we are visualizing it, and then we are getting it. And then if we could measure it, we'd get 0 0 1 1. Actually we would have got the same answer for bell 0 also, but here it comes with a phase difference. Okay, the phase difference cannot be visualized in a histogram, because histogram is just giving you how much probability of each state. Okay, it won't give the minus or plus sign. Okay, to visualize the phase changes, we'll have to move on to Q sphere. We'll see it further. Okay, yeah. So the running may take time. Okay, that's why I'm not running it again and again. If you run this slide again, you'd get a different one with probability terms. Okay, I'm just not running it because, you know, if it got stuck, the whole session time would be, it should be extended, so still it comes. So I'm just running it with as I've already run it. I'm just showing you what my outcomes were. You could try it on your own, and when you could again and again, if you run the same circuit one time, this won't stay 480 and 520 forever. The next time it could be 560 here and 440 here. Anything could happen. Okay, but it would be in and around the circle of 500 to 400. Okay, you can keep 500 as the center of the circle, and with the radius alone it would move. Okay, there wouldn't be much difference, but there would be difference because calcium simulator mimics the real device. Okay, that probabilistic answer would change for each and everything. Okay, yeah. So we are moving on to the last bit state. The input should be 1 1. So when it's 1 1, again we are creating the quantum circuit. It's the same thing again. So as it is 1 1, we have the X gate in Q0 also. We have the X gate in Q1 also, and then we have H and CX accordingly. So yeah, so as I told you, the must for the entangled state, and in all these 4 states, we had H and CX correspondingly, H and then CX correspondingly, and then we played with these X gates. Okay, that's it. We could play with Z gates also. You know, this is not the only way to create these 4 entangled states. Only that's common is that H and CX. If you could put in H and CX gate, you have already created an entangled state. And then you could play with X and Z gates anywhere to make these 4 entangled states. You know, like wherever you put those Z gate and X gate, you would fall into any of the 4 entangled states only. Okay, you couldn't create more. But if you could entangle 3 qubits, you would get a GH6 circuit, and then 4, and that would be of higher levels. Okay, for 2 qubit states, we have just these 4 entangled states. Okay, and then we are measuring bell 3 accordingly. See, you could get 492 and 508 here for 0 1 plus 1 0. Okay, 0 1 minus 1 0, but we wouldn't have the phase difference here. And see, this probability is really close, 492 508 508. Yeah, sometimes it could be even 499 501, but at least by 1% or one thing, one would beat the other, because Castle simulator wouldn't give you the exact answer. The probability would collapse it to 0 1 or either 1 0. It could collapse between those things, but if you could again measure it, we'd have something different, okay? And then Qiskit representation, okay? Still now we didn't get the difference between the space changes, as I said, right? Between that minus sign, we couldn't see them, okay? Like, Rohini, where is it? Where could I see them? This is the bell state 0 and bell state 3, bell state 2 have the same answer. Bell state 1 and bell state 3 has the same answer. So where could I see the difference? And we have Qiskit representation to the rescue. Again, we are creating the bell state, and then we are getting state vector. These are all the codes. You could, for the exam, these codes are damn useful, and yeah, because you would definitely have coding questions there. And then you get the state vector. The state vector representation is also equally important one. And then when you plot state Q spirit, you have 0, 0, 1, 1 here. Okay, this represents the phase changes. As we have no phase changes, it shows blue color for us. Okay, yeah. And then we have bell state 1, bell state 0 is completed. Now we have bell state 1. So according to bell state 1, what answer should we get is 0, 1 plus 1, 0 with no phase changes. And yeah, we get these state vector representation. And now we have 0, 1 plus 1, 0 without any phase difference. Okay, the phase difference is 0. Yeah. And then bell state 0 is completed, bell state 1 is completed. We are moving on to bell state 2. Okay, so bell state bell 2. Okay, when we are moving in, so we, according to this, we should get I think 0, 0 minus 1, 1. So now we are going to visualize our phase change, how it's going to show us. Already you would have seen in the slides, but for you again. Yeah, 0, 0 minus 1, 1. Okay, we have a phase difference here. Okay, yes. And then we have bell state 3. It's x. Yeah, the input should be 1, 1. We've seen it in the before only. So we are getting the state vector. State vector also I've already explained to you in the slides. The same thing it would be. This J you need in mind because this is the imaginary part of it. It doesn't play an important role, but this minus sign here plays an important role. Okay, because that represents our phase change. Yeah, so it would be 0, 1 minus 1, 0. Yeah, yes. Okay, so the phase change. So yeah, and next is our unitary representation. I'm not diving deep into unitary representation. Like, you know, it takes a lot. It involves some maths and thing. Maybe, like, you know, we'd come into it to another session because it contains a lot of information. You know, when I took the test, I attempted for the first time and I failed. Okay, you know, at the point, you know, the point where I failed was this unitary representation. This fellow, you know, he's such a fellow, like I failed in this unitary representation, and again I took a week again. I prepared the same thing. I just, you know, like everything else I was okay ready a bit, but this unitary representation was the only thing I prepared in the whole week. And then when I gave the exam, I passed it. That's it. So he's such a fellow. Like you need to pay if you want to clear the exam. The examiner's favorite choice of question would be unitary representation. Okay. So yeah. So like a bell again for bell 0, the same for our bell 0 state. We have this unitary thing. Okay, I'm not diving deep into it. I just want to show you that there is such a representation which comes in the exams, which is very, very important. Maybe in another session, I would like to explain it in deep to everyone. Okay, this is similar to, you know, it involves tensor product and dot product and all. So with the clear slides, I'd like to explain it because, you know, unless and until we are explaining it clear, it would lead us to confusion, and because of the confusion, you know, like we may not end, we may end into different conclusions. Yeah. So this is the bell state this is the unitary representation for bell state 0, and then for bell state 1, for bell we have the unitary representation as such. You know, it's a 4x4 representation. You could take the 0.707 out, you could put it as 1/√2. You could see it's kind of big thing, but I want you to put more concentration into it. Maybe we could have another session just for unitary representations. According to me, it's an important topic. Yeah. And then we have Bell State 1. We have the unitary simulator. We put it in the unitary simulator, and then we get the answer to be this. You know, like in the exam, we'll have to memorize this because they won't ask directly what is the unitary representation with this. They'll ask questions. They give you the unitary representation. You will have to perform it with various gates, various circuits, and then you'll have to give the answer. Okay, that would be the thing. So even if you could note down these representations, it would be useful for you now. But this representation, you needn't memorize it. If we could have another session, we would definitely crack them out, and we could, you know, just by having tensor products and dot products with our representations, you know, the HCX, HXCX, we could get it. Okay, yeah. So for Bell State 2 again, so Bell State 0 is over, 1 is over, 2. Okay, now for 2 we have this as the Bell State representation. Yes. And then for Bell State 3, the last Bell State, we have this as the representation. There's a lot of signs also, you will have to notice it. You know, here it's everything is plus, but you have a minus sign here, you have a minus sign here. So you'll have to notice it. Okay. And then we have, you know, as I already told you, the block sphere. You know, block sphere is one of the, when I first started quantum learning in my Q cross Q course, okay, that's where I got the introduction. I visualized everything, you know, those gates, the X gate turning, the Y gates turning, the Z gates, rotation around, everything everything I visualized with the block sphere only. I did not use the Q sphere. What we saw now was the Q sphere. But to visualize the X gate, Y gate, Z gate, and all other gates, we use the block sphere only. So, you know, like he was my old friend, one of my old friends. You know, whenever I used to get a doubt, he was the one who used to solve it. You know, when I could put the gates, he beautifully rotate it around the block sphere and give me like where this X qubit would land to, where this 1 qubit would land to. He would give me such good answers. But to my surprise, you know, when what happened to entanglement is, if you run an entangled state and if you visualize it on block sphere, you're running the basic entangled state, you're visualizing it on the plot block multivector, and you wouldn't know where the qubit stands. Okay, you would just get 2 qubits with a red sign in the middle, indicating that qubit 0 and qubit 1 are entangled, but you wouldn't know between where. So, you know, block sphere, as how Einstein was, block sphere also got confused between where are those states. This is also one of the most important questions in your I got a question. Okay, so that's why I'm saying it. So you would get the exact question like this, okay, where, you know, it could be like arranging them in order, and the last one will be, you will be applying a plot block multivector, and what would it result to? It would result to this. Okay, this could come as even your direct question. Okay, you know, that easy marking question, you will all have that one question, right? That would be this. You know, what would be the visualization of a block sphere in a entangled state? It wouldn't visualize it, but you will have 2 qubits with a red color sign in between. Okay, red color, you know, pointer in between. Yeah. So yeah, from this our lab session also gets over, and I will go on to PPT. We'll have some 2 more slides, and then we'll move on to the demo session. So still now I've told you things about quantum entanglement, and how many states are there, why is it so unique and all. But you could ask me like, okay Rohini, you're telling me everything, okay, it's fine, Einstein was proved wrong, and there was a awesome scientist who proved Einstein wrong, okay, everything is fine, all these states, all these visualization techniques, but where do we use this quantum entanglement? Such an exciting, such an exciting thing. Where do we use it? Okay, for that the answer is superdense coding. Okay, superdense coding is about efficient information transfer. Okay, but why is this important? Okay, in the year 2020, okay, the lockdown year, okay, if you could take, the average rate at which data was generated in the world was 600 Gbps. Okay, it was 600 Gbps, and the data which was generated was 600 Gbps, and the global average internet speed was approximately 30 Mbps. Okay, see the difference. The data is equal to 600 Gbps, but the average internet speed, okay, it was 30 Mbps. Okay, so which is almost 20,000 times slower. Okay, so it was in the year 2020, and now we are in 2023. Okay, and in the upcoming year we are going to generate more and more data, and it becomes increasingly difficult for information transfer. Okay, I'm sitting here, I have my data, okay, and a person who's somewhere, my friend is somewhere, okay, and his data is also, he also has his data, but we have some some tight information, we have some very important information, but the the internet speed is damn slow. So because of that, we're not able to get our data. Okay, that would be really frustrating, right? In our cell phones or in our mobile, if we get our data, like if the internet's not working, that feeling of frustration, right? So that feeling would develop further. That would be the case. Okay, with the data would be generated in a more manner, but the internet speed would be going down. Okay, so that would be the case, and that would be extremely difficult, right? So who comes to the rescue would be entanglement. Okay, in superdense coding, superdense coding is one of the major applications of entanglement. Okay, so quantum key distribution is also major application of entanglement and superdense coding. So we can use, so in superdense coding, what we use is we can use we can use entanglement to communicate the same information by sending half as many qubits as classical bits. Okay. So that by sending one qubit, we will transfer 2 bits of information. So that's cool, right? Like for 8, we have to transfer 8 bits of information. We would just send 4 qubits. For 16, we would send just 8. Okay, so for 400, we could just send 200 qubits. For 400 bits of information, we could just send 200. So that would create for 1 lakh bits of information, we could just send 50,000 bits of information. So instead of sending 1 lakh qubits, 1 lakh classical bits, we could just send 50,000 qubits. That would be really cool, right? So that lack of internet speed would be solved. Okay, so using the same technique, we could have the required speed for our information transfer. Okay, but superdense coding and all, we are working because the qubit itself is the section of qubits itself is in under construction, because as a qubit we have some limitations also. How much ever quantum has advantage, quantum has some disadvantages too, because it needs absolute cold temperatures, and we should have more number of qubits. Okay, we couldn't just generate it's fine, it's absolutely fine that we need just 50,000 qubits to send 1 lakh bits of information, but creating 50,000 qubits is not an easy task. Okay, and I think every one of you here can help the community build such more qubits, and that's what our work is, right? Einstein and Newton and John Bell and many other scientists did their works. Dr. Oppenheimer, okay, like I recently got the name, I didn't know him before, so yeah, so they did their work accordingly. But what about us? Okay, we should also contribute to the community, right? So, and that's why I think we are here. Okay, we could that wouldn't be direct. We have to do a lot of research and we have to learn a lot about quantum computing. And maybe our future could one day have 50,000, 50 lakh qubits. Okay, so many qubits, and we could transfer information at a very fast rate. Okay, QKD, quantum key distribution, is also one of the main important. I don't have a slide for it, but that's also a very important application of entanglement. You know, it's very important for the cyber security. Once we get quantum key distribution into action, no one could ever hack our passwords or thing, because you know it has such a cool thing inside it. And maybe one day also we could have QKD and super encoding as sessions also. Both of them are really interesting topics to work on. And I think your quantum key distribution is would be like, you know, would be the first, most probably I think so, would be the first application of quantum to be in action, because you know there are a lot of people working there in the field. And cyber security is one of the main fields which are going to be affected by quantum, and mainly in quantum mechanics it's going to be affected by quantum entanglement, because QKD has quantum entanglement as its base. Okay, so yeah, you know, like we could share our information. Our country could have a very secure passwords, and a more secured information transfer. Our bank passwords could also be very secure. So from this we are covering up our session. So what and all we saw would be here. So objects which are entangled share a defined relationship. Okay, that's what we saw there. And the measurement on one qubit affects the other qubit. And entangled states cannot be factorized. And we saw the quantum entanglement and Bell states. And then we saw the code for creating all the Bell states. And then we saw the visualizations like the histogram, state vector, Qiskit, state city, state hint, and state polyvector, and mainly block sphere. Okay. And these are some references. Okay, if you are really interested in quantum computing, you could visit all these sites. And there are also many upcoming challenges and many things going on from IBM side. Like we have quantum explorers going on. QGSS recently, Quantum Global Summer School 2023, from theory to implementation, recently the sessions got over, and we are having time for for the lab sessions for us to complete. But Quantum Explorers is if you really wanted to get into quantum computing, I think for now Quantum Explorers would be a great place. It's a game-based. It's a self-paced game, and you can register anytime now, and you'll have time till February. Like you know, it's an interstellar journey. You would be going on an interstellar journey, and you can unlock batches, and by unlocking batches, you would automatically be learning quantum computing as a game. And Dr. Radha Pyari, our India community lead at IBM, is connecting is the organizer for that. That's a very interesting one, you know. And if you are really interested in quantum computing, you could join one of them for now, Quantum Explorers. And then Q coding schools lessons will also start from October, I think so. The brochures and vouchers will be available soon. We could that one is also a great place to start, because I started it there. They're awesome people, and they're just awesome. Yeah. So for you to reach me, you can reach me at my email ID, and then it's my LinkedIn ID. Yeah. So any doubts or any queries or anything, if you want to reach me, you can reach me here. Thank you. So yeah.
Thank you, Rohini. I think this was a fantastic way of showing what quantum entanglement is, right? And Deepa, over to you.
Okay, sir. Before that, there is a question in the chat window. Yes. Shall we go to that?
Yes.
Okay. The question is, what's the significance of negative state?
Okay. So, like we are creating the bell state, okay? So when we are creating the bell state, we have the negative sign as well. So it's like, it's from, as our scientist and said, for us to create the bell state, 0, 0 plus 1, 1 is a bell state, 0, 1 plus 1, 0 is a bell state, 0, 0 minus 1, 1 is a bell state, 0, 1 minus 1, 0 is also a bell state, There are 4 bell states, The negative state signifies the phase change, nothing but the phase change, okay? We are mentioning it negative because we have to have a difference between bell state 0 and bell state 2, right? We have to have a difference between bell state 1 and bell state 3, okay? We have 4 bell states. So bell state 0 gives us 0, 0 plus 1, 1, okay? And bell state 3 gives us 0, 0 minus 1, 1. If we didn't have that minus change, won't these both states be the same? Okay, this minus state signifies the phase change. The phase change, as we visualized it in as we visualized it in Qisphere, you could see the phase change. The phase change is nothing but the rotation. Okay, the rotation about the Qisphere. Okay, that's it. So the negative sign represents the phase change. Okay, just for us to show there are 4 different bell states.
Okay. There's another question, Rohini. That is, we know about qubits, but does not have clear idea about applications of qubits. Is qubits okay?
So
Can you please explain?
yes, okay. I'd want you to imagine as as a stack, okay? So first at the stack, at the bottom of the stack, we have a qubits, okay? And then the above of the stack, we have a gates, okay? You can take the normal classical thing also. We have the qubits, and then we have the gates, and then we have our algorithms, and then we have our applications. Okay, this is the stack. Okay, so for us to go into applications, first we need to build up our qubits. Okay, there's no such thing as application of qubits. Building on qubits, we get our applications to be done. Okay, our qubits are not yet ready. Okay, they need absolute temperature, absolute temperature in the sense zero Kelvin, because they cannot take up noise, because the qubits are very sensitive, and if they have noise they would confuse themselves and they would collapse. So we have qubits, and then we'll have our applications according to it. So if we could build our qubits correctly, we would have our applications on ready. Like if we could build our qubits correctly, we could have 50 qubits, 127 qubits, 356 qubits. We could build up on our qubits. They should be at absolute temperature. Attaining an absolute temperature is a little bit difficult. Yes, and then we have to increase the number of qubits, and then we could use them for our applications. Yes, okay, yeah.
Okay, they have told that it's not qubits, it's qurits, qutrits, QUTRITS.
No, it's qubits only.
Okay, then next one, next question. Can you explain the output which shows phase representation circle once more, the one which had circle?
Okay, so you're asking me the Q-sphere representation. I hope so. Am I right? So this is the block sphere representation. So we'd have nothing. We have just two qubits entangled, and the Q sphere representation would be 1 second. Yeah. So for bell state 0, we'll have this as the Q sphere representation 0, 0, 1, 1. And then for bell state 1, we have 0, 1 plus 1, 0.
Share your screen.
Oh, sorry. Just a second.
You can show it in IBM Composer if you can.
Yes.
So yeah, so maybe we could move on to the composer as Ma'am said. So here, this is the composer, okay, where we could just what do you say? We could just play with our gates here. You know, it would give automatic results. So as you asked me for the Q0, I mean, for as you asked me for the bell state, so first I am dragging my H gate, I'm creating a superposition, and then I'm having a CX gate, and then see if you could look here. I think it's visible. So yeah, so we have 0011. I don't think it's clearly visible. You know, it's somewhat short. I think so, but maybe I could just extend it. Yeah. Okay, 00 and 11. Okay, the same thing in our notebook also. 0011. Okay, I run it on the composer with just to show you how it works. And now if we could create bell state 1, we have X gate here. This is the X gate. Yeah, so now we have 0110 with no phase changes. Yes, the notebook also. Yeah, and then we in the notebook also we could see it 0110 for a clearer view. I'm just showing it here with no phase change, and then we are putting the input as 10. So this would be here. So now we have a phase change. Can you see it? 00 minus 11. I think it's a little bit wrong here because we have 00 with a phase change. Don't mind it here. Just see it here. We have 00 minus 11. Okay, is it clear? 00 minus 11. You know, the state is also the same. 00 minus 11. And then now we have for the fourth gate, I think it's here. Yes, we have 10 minus 01. Yeah, that's it. Okay, that's it. Hope I'm clear. Uh, okay.
Okay, and there's another question, not question. Can you please show the slides which had email again?
Sure, my email ID is Rohini Venugopal073@gmail.com, and for you, it's here. Yeah.
Or you can paste it in the chat window or anything.
Yeah,
It will
sure.
be more useful.
So yeah, and this is my LinkedIn ID, or you could just search me on LinkedIn and you could.
Okay, any other questions? Participants, will you please on your video let me take a screenshot.
My email ID, I've posted in the chat. So my reason to be here is like, you know, I want to say like the community is super helpful in quantum computing. Okay, so there are you know, there are numerous challenges in this field, but if you really wanted to be in this field, you know, there are a lot of community members helping you, and if it's not them, I would definitely not be here because, you know, like I'm young and they had that potential to attract me into this field. So if any one of you is wishing to come into the field, there's a lot of potential and there are a lot of people, you know, besides I used quantum as my escape reality to escape my reality from school and from all those math and physics and chemistry. I did it in my maintain like in my 11th standard, you know, like this was my stress buster for to say, you know, it's such an inspiring field to be in, it's such an exciting field to be in. So I want more members to come into the field, and if you could think, oh no, quantum is a really spooky field to be in, it is, but we have to build the future of quantum computing. So, and there are a lot of members, there's a lot of communities happening, there are a lot of events happening, there are so many events progressing, coming, and everything, each and everything is exciting. The summer and all, IBM gets all excited, it launches summer school, quantum explorers, we have spring challenges, we have fall challenges, everything is exciting. You'd get different questions and all, and you would have a team to discuss with it, and it's such an awesome place to be in. And girls in quantum, we're all girls of my age, younger than me. Our founder, Elisa Torres, is a girl younger than me. She's 17 years old, I'm 18. She's leading it worldwide, and we've got recognition everywhere. So I want many underrepresented people to come up, because we want quantum to be available for everyone. Okay, not like there's a lot of equality in quantum, I would say. Comparatively, every time, like girls are more encouraged. So persons from backward countries are more encouraged, and everyone could have quantum, and everyone could use its advantage in the right manner. Yeah. Thank you. So any other questions are also welcome.
Okay. So shall we end?
Yes, absolutely. So thank you, Rohini, for Deepa, over to you for the closing remarks.
Like thank KG sir for for contacting me, and for encouraging me in this field. I could give a session, it would be great. I thank KG sir so much for it. I thank Deepa ma'am, Pradeep sir, and everyone here for joining with me. I thank Manjuna ma'am also. So she's been a great support for me, and the team, and everyone, and all the participants for slowly encouraging me myself to handle a session. And thank you so much for everything.
Okay. Now, once again, I'm here, Deepa, and I'm honored here to give a small auto thanks and for this wonderful section done by Rohini on the section or on the topic quantum entanglement. Rohini, you did a wonderful job of explaining the topic in a way it was accessible, both engaging. So your explanation about the entangled particles and its separation, and your explanation about a large distance and how it is being connected each other, everything was very informative and thought-provoking for most of the participant, and a person like me, those who are just hearing about quantum computing. It was very interesting, and the way you discussed the potential applications of quantum entanglement to for the communication and quantum computing was also very interesting, and you helped us to understanding the importance of the topic. I would like to thank again you for this wonderful presentation. And again, we are, as you have informed us, we are eagerly waiting for another wonderful section by you, and we will be informing the date for you, which you can take over for rendering us a wonderful topic again. Then before that, I would like to express thanks from our team, that is from KG, Pradeep sir, and all our team members of MyQuantum for accepting our invitation at the last moment due to some reasons. Then I would like to express my gratitude towards Manjula ma'am, also for a great support that you have taken for us to have this wonderful section. And here we would like to thank all the wonderful participants who have joined us, and the questions you have rendered, and that could be answered by Rohini. Then before ending this small vote of thanks, I would like to ask apology to all the participants for having a change in this section. It was due to some unavoidable traveling by both the speakers, that is Abigail and KG. They had an unavoidable travel. That's why at the last moment the topic was changed. But the same topic, that is quantum inspired algorithms, we will be conducting it coming. That means any one of the coming sections, the same topic will be handled. So we expect your great support during those sections also. Then and I thank all my team members for supporting me for all the way to this date. Thank you all once again. Thank you, Rohini. Thank you, Manjula ma'am. Thank you, Pradeep sir, and my team, and all the participants, those who attended today. And we all would like to have your all feedbacks, because your feedbacks is our success. Thank you.